Welcome to Einstein's Mechanics, and today we are dealing with Newton's laws of motion. In the episode 1, we saw that dealing with mechanics, the conditions should be at rest or should be in motion. And Isaac Newton proposed some laws of what? Motion. And we'll be interested in them, saying they are going to guide us throughout our course. Let's look at the first law. And the first law is saying that if the resultant force acting on a particle is zero, the condition is zero, the particle will remain at rest if originally at rest, or will move with constant speed in a straight line if originally in motion. So what this law is saying that if I have a particle, let's look at this figure. If I have a particle where the resultant force acting on it is zero, the particle will remain at rest. And yes, this particle has forces acting on them, or this particle has its forces being resulted to what? Zero. Let's look at it. F1 and F2 are equal. So if you want to sum them, it is going to be F1. If I'm taking this direction to be positive, this will be negative, minus F2. Since they are equal, I'm going to get zero. And looking at the vertical, this is the summation of forces on the X. And looking at the summation of forces on the Y, the vertical aspect, I'm going to also have it on the Y, mg, which is the weight of the block, and the reaction, the normal reaction. Since they are equal, I'm going to have the weight minus the n should be also what? Zero. And this block will be acted upon by what? Forces, which resultant will be zero. And what Isaac Newton is saying that this block will continue to be at rest. It will be at rest. It will remain at rest until an external force what is acted upon. Or we can take it that if the resultant force acting on the particle is zero, the particle will remain at rest or will move in a constant what? Speed if originally in motion. Let's look at this figure. This figure is in motion. Yes, it is in motion, meaning there is a force what? That caused the motion. And if the resultant force acting, let's assume they are resultant, let's assume there is a reaction force here, and this is the force that caused the motion. And if the summation or the resultant of these forces, the overall forces acting on this ball, rolling ball, is zero, then this ball will continue to be what? In motion until it is being what? Acted upon by another external force to cause what? A rest to the body. It's very simple, meaning anytime a block is at rest, the summation or the resultant force on the block is what? Is zero. And it will remain at rest. If I want to lift this block, I have to add another force, an external force, which will what? Cause a movement of this block. Another force, F3, it will cause a movement of this block. If I want to stop the motion of this rolling ball, then I have to apply a third force to cause what? This ball to be at rest. So Newton was just telling us that anything in motion will continue to be in motion until it is being was stopped by another force. Or if the resultant, you talk about resultant force, how to find resultant force. If the resultant force on the body is zero, then it will continue to be in what? Motion, which is quite interesting. This will help us in mechanical what? Analysis. It will help us to know how things are going to behave if the resultant is zero. Let's look at the second law and we make deductions from there. The second law. So this is what the second law is saying. It says if the resultant force acting on a particle is not zero, the particle will have an acceleration proportional to the magnitude of the resultant and in the direction of this resultant force. So this second law gives us the relationship between the motion of a particle and the force acting on it. This Newton's second law was quite interesting. It gave us the relationship between motion and the force causing the motion. So another way we can state the second law is that the rate of change of linear momentum is proportional to the applied force. So let's say this is the applied force, and the law is saying the rate of change of momentum is proportional. This is a proportional sign to the what? Momentum, mv, the rate of change. So we have a change, that's what? Time rate. So this is the second law. So the rate of change of linear momentum which is mass times what? Velocity, is directly proportional to the force applied, and it takes place in the direction of the force. From here, we can now find the relationship between motion and the force. So we can make a deduction that the force can be equal to, since the proportionality is removed, we can have a constant k, and I still have the mv, which is the momentum on what? dt. Are we good? We know that mass is constant. Yes, mass is constant. Mass is what? It's a constant. So meaning this change or the rate is affecting the velocity alone. So meaning I'm going to have my force is equal to the constant, the mass out, and the dv dt, where dv dt is the same as change in velocity, where change in velocity with respect to what? Change in time can be v2 minus v1 on what? T2 minus T1. And change in velocity will result in what? Acceleration, which is what? A. So meaning dv dt will give us the acceleration produced, A. Okay, so this is force is equal to a certain constant k, mass times acceleration. And if K is unity, then we are going to have a force applied to a body should be the mass times its acceleration. So from Newton's second law, we were able to deduce that the relationship between motion and the force applied is giving us this equation, the product of the mass and the acceleration, the rate of change of linear momentum, where linear momentum is mass and what? Velocity, and the change, the time rate, the t, a certain change. And since mass is constant, the rate or the change is affecting the velocity. Anytime we have a change in velocity, we are getting what? Acceleration. So this whole dv dt can be acceleration. So we are having F, which is the force applied, equal to a certain K, ma. And if we consider K to be unity 1, then the force applied is equal to mass times acceleration. So generally, force is equal to mass times acceleration. And this is our first formula we've obtained during this course. And throughout, we'll be using this formula, mass times acceleration, to calculate for force. We will solve examples and we see how this works. Let's look at the third law of Newton. Newton's third law. I like this law a lot. It's interesting. Let's look at how it works, or what Newton said. The third law, it states that the forces of action and reaction between bodies in contact have the same magnitude, same line of action, and opposite sense. Or this is the simplest one. To every action, there is an equal but opposite reaction. To every action, there's an equal but opposite reaction. So let's look at this block before I use the images to explain. I have this block and I am applying a certain force P here as P1. And Newton is saying that anytime I apply a force P here, there is going to be an equal force opposing the motion of this force. That's what? In the opposite sense, meaning in the opposite direction. So I can have a force opposing this force this way as another P1. So we can see that these forces are equal in magnitude. If this is 10 Newton force, this is 10 Newton force, but they are in opposite direction to keep the system in equilibrium. So let's look at this diagram. This is a simple diagram. Then mostly we call it what? A seesaw. That's the simplest name we can what? Remember. So this is a pivot and we want to balance. The moment there is an action starting from this place, first the application was here, it started here. It will try to what? Bring down the system, bring down the system. And as it is doing so, there should be an opposite force but equal in magnitude. So the opposite force will try to what? Pull this up because this one is coming down and this will be what? Up. If this force has 20 kilonewton force, the upward direction is same 20 kilonewton force, which is interesting. So this is the third law. To every action, to every action. So let's assume I want to what? Push. Let's look at this diagram. This lady is trying to, or this gentleman is trying to what? Pull back this. So he's bringing it back. And to every action, there's an equal but what opposite reaction. As he's trying to pull it back, there's a reaction force also occurring here. So as this leg is bringing it this way, there's what? A pull by what? Either the water is also trying to pull this back. And this law is what? Quite simple to every action. So this helps us to design mechanical what structures so that we can know that what force are we going to use so that we will get the right what work done. Are we good? We also have an idea that to everything we do, there's going to be what? A reaction. And the reaction is going to be equal. And most of the times, these reactions can be useful and they can also cause what? Distraction to our structures. And Newton helped us to understand this theory, which is interesting. So basically, these are the laws of motion proposed by what? Sir Isaac Newton. From these three laws, the second law will help us to what? Solve certain problems. But the first and third law is giving us a general what? Knowledge about anything we do. That's quite interesting. So from the second law, we saw our first formula that mass is that, and we got it. Let's look at Newton's law of gravitation. Newton's law of universal gravitation. Yes, Newton did a good job in the field of mechanics. Let's look at the law of universal gravitation. It says that every two particles of matter attract each other with a force which is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. It says every two particles of matter. So if I'm considering two particles of matter, let's consider this particle A and particle B. For every two, so we're taking the two of them, A and B, attract each other with a force which is directly proportional to the product of their mass and inversely proportional to the square of the distance between them. Meaning this particle A has a mass, let's say m, and this B has a mass small m. And as these two particles are existing, there is going to be a force pull. So this one is trying to exert a force Fa, and this B is also trying to exert a force Fb for every two particles. So if I have another particle C, which is, let's say, mc, with a mass mc, this m will try to exert a force Fc, and A will again try to exert another force Fa on them. So every two particles we have in existence, they try to what? Pull themselves, or they try to exert some force onto the other. So we can consider a human being and the earth. Anytime we are walking on the earth is trying to what? Exert a force, a pull on what? The human being walking. And your body is also trying to exert a force on the earth. Let's look at this balls or these circles. So we have M1 and M2. They are objects. So that's object 1 and object 2. And what Newton is trying to explain to us, that as these objects are existing, they are just there. They don't know anything. But what they are actually doing is that they are exerting a force onto each other. Knowingly or unknowingly, they are exerting a force onto each. So you can see that the mass 1 is exerting a force F1 on the mass 2, and the mass 2 is also trying to exert a force F2 onto the mass 1, and it happens between every two objects. And if we want to calculate this force, if we want to know the magnitude of this force, then the formula comes in, where Newton is saying that to know this magnitude of force, where they exert, F1 is always equal to F2. The force they exert on each other is the same. So this Fa is equal to this Fb. So Fa is also equal to what? Fc. They exert equal amount of what? Force. So this force can be calculated from the definition. We saw that the force, which is directly proportional to the product of their masses. So the force exerted between them is directly proportional. So let's say directly proportional to the product of their masses. So let's use this mass 1 and mass 2. Mass 1 and mass 2 to the product of their mass, and inversely proportional to the square of the distance between them. Let r be the distance between them. So inverse to the square of the distance between them. So since we have a proportional sign, we have to introduce a constant, meaning the force acting between any two objects is given as a certain g, the constant, the mass 1, the mass 2 on r square, which is the distance between them. And this is the formula Sir Isaac Newton gave us. So we can see that as two objects are there, the force between them becomes greater anytime the mass increases, because this is M1 and M2. Anytime any of M1 and M2 increases, it's going to cause an increase in the force, because it is directly proportional. As M2 or M1 increases, the force increases. And we can also see that anytime the distance between two, let's say this R is 2 centimeters. Let's assume 2 centimeters. Anytime the distance between two objects increases, it is going to cause a decrease in the force between these two particles. So objects with a distance between them of 2 centimeters will have a greater force than objects with what? 4 centimeters. Because it is going to be what? Inversely what? Squared. R squared. This is going to cause a decrease in the force. So this masses M1 and M2 has a distance 2 centimeters between them. Will exert, let's say, if the force between them is 40 newtons, then we try to decrease the distance between them. So this is it. We have M1 exerting a force. This is M2. It's also exerting a force. And now the distance between them is 0.5 centimeters. Now the force acting F that exists between these two particles or these two bodies is going to be greater, way greater than this 40 Newton. And it is greater than this 40 Newton because the distance between the two particles of equal masses or of the same mass as figure or as in what this figure 1, this mass is equal to this and this m2 is equal to that. But now the distance is decreased, which is going to cause an increase in the force that exists between them. So anytime we are making mechanical structures and we are going to make or we are going to consider the force between them, we will see that anytime the distance between the objects increases, an increase in the distance will cause a decrease in the force. But a decrease in the distance will cause an increase in the force. And let's take note of this. Where this G I introduced as a result of the proportional sign is a constant, and it is known as the universal gravitational constant, and it is found from experiment that its value is 6.673 exponent negative 11 meter cube per kilogram second square. So that's the value. It's a constant. So whether you are given or not, you just have to know this constant of what? Universal gravitational or G or the universal gravitational constant. 6.673 10 to the power negative 11 meter cube per kilogram second square. And that's the gravitational force of attraction F acting between two particles M1 and M2 at a distance R apart is given by the relation F. So this is the relation, this is the formula given. So this is our second formula. So this is our second formula from the gravitation law. First, we got our first formula from the second law of what? Newton. So we've gotten two equations here. The universal gravitation law gave us one formula which says the force is equal to the gravitational constant, the product of the masses, and the square of the distance between them. So if you are given the masses and the distance between them, straight away you can calculate for the force acting between any two particles. So you can conduct an experiment and find your mass, find the mass of your friend, and check the distance between you and use the gravitational constant. You can now know the force between the two of you, and it's quite interesting. So we pay attention to that. Thank you for watching this episode. This was about explanation, and we are going to solve questions, about 6 questions on these two formulas that we've obtained in these two episodes, and it's going to be interesting. We're going to solve questions. So check out for the episode 3. This is basic mechanics, and we are taking you through gradually. It's interesting. Subscribe to the channel and drop your comment. Thank you for watching. I am Brown.